So chapter 5 is a more or less a graphing chapter. Most of what we're going to do is going to involve graphing, and you're absolutely going to want to have your graphing calculator handy because a lot of what we're going to do in this chapter is really you'd have to solve it by using calculus if you want to solve it algebraically. So we're going to learn some calculus concepts and use our calculator because we can't do the calculus here. There's a handful of concepts that I need to explain before we get into the problems from section 5.1. The first concept is called multiplicity. And maybe more specifically, multiplicity of a factor that gives an x-intercept on a graph, or creates an x-intercept. And I have a handful of problems that I created to help you understand multiplicity and how they impact a graph. This is entirely a graphing section, so kind of everything is going to be focused on how the concept relates to the graph of a function. So I started off and I graphed the simple parabola y equals x plus 6 times x minus 7. Very specifically, I only labeled 2 points. I labeled the x-intercept negative 6, 0, and the x-intercept positive 7, 0. If I wanted to find the x-intercepts by hand, which is going to be a skill that we're going to need in this chapter, I would just take the function, set it equal to 0, and because it's factored, I'd split the factors apart, set each factor separately equal to 0, and do the algebra to isolate the x. The algebra to isolate the x gives me the x-coordinate of the x-intercept, and I have to know that the y-coordinate is 0. That's review, but it's going to be important. What's going to be new and important is the concept of multiplicity. And the multiplicity of a factor is the exponent that it has as I'm going once the polynomial is factored. Both the factor of x plus 6 and the factor of x minus 7 had an implied exponents of 1. So when I typed some stuff down here, I said the x-intercept of negative 6, 0 has a multiplicity of 1, which means the exponent that created the x-intercept of the factor had an exponent of 1. Similarly, 7, 0 has a multiplicity of 1. When it comes to multiplicity, not so much the number that the exponent is, but whether it's even or odd is a big deal. So I parenthetically, or after a comma, I said negative 6, 0 has a multiplicity of 1, which means the exponent that created it was odd. Similarly, 7, 0 had a multiplicity of 1, which meant the exponent that created it was odd. The oddness or evenness of the multiplicity is going to impact what the graph does at the x-intercept. And when a factor that creates an x-intercept has odd multiplicity, the exponent is an odd number, but the graph will cross the x-axis at the x-intercept. So at both the points negative 6, 0 and the point 7, 0, when the graph approached the x-intercept, it went straight through to the other side of the x-axis. That doesn't have to happen. I'll show you in the next example what could happen when we don't have odd multiplicity. So for each of the two exponents, they both have odd multiplicity, or multiplicity of 1, and at each of the points on the graph, each of the x-intercepts, the graph physically crosses the x-axis as opposed to not crossing. And let me show you what I mean by not crossing here in another example that's remarkably similar with just one small tweak to the exponent. So in the next problem, I created a graph of x plus 6 times x minus 7 squared. This is going to have the same x-intercepts. To find the x-intercepts, you would set the factored version of the function equal to 0, and it's enough just to set the insides of the parentheses equal to 0 to get my x-intercepts. The x-intercepts are going to be the same. The x-intercept from the x plus 6 factor is going to be negative 6, and you can see it down there. There's the point negative 6, 0. The x-intercept from the x minus 7 squared factor, the x-coordinate is going to be 7, and you can see it down here. You can see 7, 0. When I look at the exponents of the factors, the exponent of the x plus 6 factor is 1. So the multiplicity of the x-intercept that was created by it, the multiplicity of the negative 6, 0, is 1, which is odd, because the x-intercept from the negative 6, 0 comes from a factor with an exponent of 1. But the x-intercept for the 7, 0, it comes from a factor with an exponent of 2. So if 7, 0, I would say that x-intercept has multiplicity 2, because the exponent of the factor in the original problem has a multiplicity of 2, has an exponent of 2. I didn't need the exponent to find the x-coordinate of the x-intercept, but it impacts the graph. It turns out that if an exponent is even that creates an x-intercept, we say that that x-intercept has even multiplicity. So, it has multiplicity 2, which is an even number. The big deal is graphically what happens. If you have even multiplicity, the graph touches or bounces off the x-axis at the x-intercept. So we'll see at the two x-intercepts, the point negative 6, 0 came from a factor that had an exponent of 1. 1 is an odd number, so at the point negative 6, 0, the graph is going to cross and go on either side of the x-intercept. But at the point 7, 0, because the x-intercept that created it was the even number 2, the graph isn't going to cross the x-axis. This is going to touch and reflect off the x-axis. So you'll see the difference graphically what happens. The graph here at 7, 0 doesn't go beneath the x-axis. It just gets to the point 7, 0 and then keeps going, reflects off the x-axis and stays above the x-axis. So the big deal is if you have odd multiplicity, the graph will cross the x-axis at the x-intercept. If you have even multiplicity, the graph will bounce off the x-axis. I usually just say the graph touches the x-axis. Is kind of the common thing to say. I wrote another example just so you can kind of see, and I sketched a graph. This function is going to have the same x-intercepts. You would set this factor equal to 0, and you'd get x equal to negative 6 for an x-coordinate of an x-intercept. That would create an x-intercept of negative 6, 0. Setting this factor equal to 0, the x-coordinate of the x-intercept that creates it would be 7. That factor would give the same x-intercept of 7, 0. The x equal negative 6 x-intercept came from a factor that has an exponent of 2. So that x-intercept of negative 6, 0, it would be appropriate to say it has multiplicity of 2, which is even. And because it has even multiplicity, when the graph gets close to that, when that graph goes through that x-intercept, it doesn't cross the x-axis, it touches or bounces off the x-axis. The exponent for the x minus 7 x-intercept was 1, so the x-intercept of 7, 0 is 1, which is an odd number, so the graph is going to cross the x-axis. So the big difference is if the exponent is even that creates an x-intercept, then the graph will touch and not cross the x-axis. If the exponent that creates the x-intercept is odd, the graph will cross the x-axis. I have one more example just so you can see what happens if both the exponents are even. So in this fourth example, the x-intercept that comes from the x plus 6 squared is negative 6, 0. That x-intercept has a multiplicity of 2, which is an even number, which means at that x-intercept, the graph is going to touch the x-axis and not cross the x-axis. You can say the graph bounces off the x-axis just fine. It'd be equivalently good. That x minus 7 squared is going to give me the x-intercept of 7, 0. The exponent that creates it was 2. Can't even spell multiplicity. So, and 2 is an even number. So the graph also is just going to touch and not cross the axis. If you had an exponent of 2, 4, 6, or 8, the graph will do exactly that. It'll just bounce off, touch the axis, and not cross it. If you had an exponent of 1, 3, 5, 7, or 9, the graph is going to cross it. So that's the first concept. The second concept has to do with how the graph of a complex function compares to the graph of a not so complex function. If you get high enough in math, you might not know what the graph of 3x to the fourth minus 12x squared looks like. That's too complicated to just to look at it and know what the function looks like. But if I strip down it down to just its highest exponent, it's pretty common for somebody that's high enough in math to know what this graph is going to look like. And it turns out that the next concept that we're going to work with is end behavior. And it has to do with what the graph looks like, not in the middle, but on the far left and the far right edges. And it turns out that in the middle, graphs can do remarkably different things. I graphed f of x equals 3x to the fourth minus 12x squared. And in the middle, this graph has, some humps in it. It has a minimum point, a maximum point, and a minimum point. So between kind of the minimum and maximum points, the graph can look remarkably different. The graph of 3x to the fourth is completely flat. Doesn't have a maximum, well, it has a minimum point, but it doesn't have these wiggles in it. But if I get far enough out past the turning points, the graphs will ultimately do the same thing. This graph of 3x to the fourth is working its way up and to the right. The graph of 3x to the fourth minus 12x squared, they're shifted a little bit, but they look exactly the same. The right-hand side and the left-hand side of the graphs resemble each other. They look exactly the same except for possibly a shift. Kind of the 12x squared minus part shifts the graph in some sense. So I would say that when they say what's the end behavior, so ignoring the middle, what graph does 3x to the fourth minus 12x squared resemble to the outsides beyond the turning points? And a graph always will resemble the highest exponent or the leading term. In this polynomial 3x to the fourth minus 12x squared, the term with the highest exponent is 3x to the fourth. In the middle, the graphs can look completely different, but at the far edges, these graphs will always go in the same direction. In this case, up and to the left and up and to the right, depending on either side. So for this graph, I would say its end behavior resembles the graph of f of x equals 3x to the fourth. The end behavior of a graph is the same as its leading term, and in this particular problem, that's the leading term. Wrote a few more complicated examples. I wrote the function x minus 3 squared times x plus 1, graphed it in red, and I want to know if, if I get far enough to the right and far enough to the left, if I get beyond the turning points, what graph does this kind of look like? What graph does it go in the same direction, maybe have the same sort of shape as? And to figure that out, I need to find the leading term. How do I find the leading term? Well, I write the problem without its parentheses, and then I multiply the first term in each parentheses. Here, x times x times x is x cubed. That means if I get far enough left or far enough right on the graph and I don't look at the middle, other than a shifting, the graphs are going to look remarkably the same. This graph is kind of shifted over a little bit, but those graphs are going exactly the same direction. They have the same sort of bend. Similarly, down over here, the graphs are going in the same directions. They have the same sort of bends. So the graph of x minus 3 squared times x plus 1, which is graphed in reds, but has, a hump here and a hump there, or a maximum and a minimum, in between or around where the maximum and minimum points are, those graphs don't look anything like each other. This graph flattens out. It doesn't have a maximum point. It doesn't have a minimum point. But once I get beyond the maximum points or beyond the minimum points, other than phase shifting, the graphs look completely like each other. So we would say, in terms of find the end behavior of the function, this graph is going to resemble the graph of f of x equals x cubed, except for a shifting. If I wanted to know, as I get far enough out to the right or far enough out to the left, what the graph of f of x equals x plus 2 times x minus 2 times 3x plus 15 would look like, then I need to find the leading term. The leading term is the product of all the first terms in each parentheses. If I multiply x times 3x, I get 3x cubed. That means that's the leading term of this polynomial, and the end behavior of any polynomial is going to be the same as its leading term. In this case, its leading term is 3x cubed. I graphed the given function, and I graphed the 3x cubed, which is the leading term of this function if it was multiplied out. And again, you'll see between where the maximum and minimums are, these graphs don't look really that much alike at all. Here, this graph is decreasing, then increasing. This graph is only increasing. But if I get out beyond the maximums and the minimums, then the graphs start to look exactly the same, other than some sort of phase shifting. Here, they're both kind of curving up and to the right, curving down and to the left. So they look like each other. So it would be appropriate to say, if I was asked to find the end behavior of this function, I would say the end behavior, if I could actually spell this morning, I would say the end behavior is the graph resembles the graph of f of x equals 3x cubed, meaning it's going to do exactly on the far right and the far left the same things that 3x cubed does, other than the shifting. One last concept, which has to do with how many humps you could have in a graph. In this section, we'll loosely refer to as maximum and minimum points as turning points. So a local maximum or absolute maximum point and a local minimum or an absolute minimum point we're going to call these, in this section, we're still going to call them maximum and minimum points, but more generically, I'm going to call these points turning points. So the graph that I drew for f of x equals 3x to the fourth minus 12x squared is graphed here. It has 2 minimum points and 1 maximum point. So this graph has 2 minimum and 1 maximum point. So it has a total of 3 turning points. There's going to be a question that we're asked when we're going to sketch a graph, is what is the maximum number of turning points the graph could have? And the maximum number of turning points a graph can have is the exponent of the leading coefficient minus 1, leading term minus 1. Here, in this particular problem, the leading term is 3x to the fourth, which means the end behavior is going to be the same as 3x to the fourth. But the exponent of this leading term is 4. This graph can have at most 3 turning points. It actually does have 3 turning points. So when we're going to sketch a graph, if I'm asked to graph this function and I start creating a graph that looks like, like that, well, this graph has 1, 2, 3, 4, 5 turning points. That graph can't be right because this graph could have at most 3 turning points. It could have less than 3 turning points, but it can't have more than 3 turning points. I graphed the function 3x to the fourth. This graph, it can't have more than 3 turning points. The maximum number of turning points is the exponent of the leading term minus 1. This graph has a maximum of 3 turning points, but it doesn't have to have 3 turning points. When I graph this, there's only 1 turning point. It's a minimum point. So if you can tell the leading term, or the leading term, its exponent minus 1 gives you the maximum number of turning points. It doesn't actually tell you how many turning points the graph has, because this graph had 3 turning points. It had the same leading term as that, which only has 1 turning point. If I was given this function and asked what is the maximum number of turning points it can have, well, I need to create that leading term again. I create the leading term by multiplying the first term in each parentheses. So the leading term is just x cubed. And the maximum number of turning points you could have is the exponent of the leading term, which is 3, minus 1. That would say I have 2 maximum turning points. And a graph actually even has 2 turning points. If I gave you the function just generically f of x equals x cubed, it's a third degree polynomial. You'll take the exponent and subtract 1. That would tell me the graph has a maximum of 2 turning points. But this graph, it doesn't even have a turning point. It flattens out, but it doesn't do this sort of thing. This graph actually has 0 turning points. That doesn't violate this. The maximum number of turning points is the highest exponent, or the exponent of the leading term, minus 1. That tells you the maximum, but it doesn't tell you, how low. I guess you could have as low as 0 turning points. One more of these and we'll get into a part 2 for this video. There's probably going to be a part 3. This part's just all the theory that we need. If I want to find out the maximum number of turning points for this function, I'd multiply the x times 3x. I'd leave the coefficient of 3, and x times x is x cubed. The leading term for this, had I multiplied the whole polynomial out, which would be disgusting, would be 3x cubed. That has an exponent of 3. That means this graph has a maximum of 2 turning points, and it does have 2 turning points. It doesn't have to, but it can't have more than 2 turning points. That's 23 minutes of just introduction. Then I have a chunk, such a chunk of problems. This is probably going to be a 3-part lecture. So that's the theory that we need. There's some other theory, but it's just review. So we'll jump into the actual problems here on part 2.